Good morning, students. In this lecture 40th of electronics, we will discuss filter circuits. So now what are filter circuits? We have discussed about full wave rectifier, half wave rectifier and bridge wave rectifier already in our previous lectures. So this filter circuits, as we know that the outputs obtained in case of full wave rectifier and half wave rectifier, they were pulsating in nature, means they were not purely DC. Still, AC component is present in DC output, but we want purely DC output. So to convert that pulsating output into purely DC output, we need filter circuits. So a filter circuit is a device which removes the AC component of the output of the rectifier so that only DC component may reach the load resistance RL. So this is the block diagram of a filter circuit, that how filter circuit it is connected to the rectifier. So the output of the rectifier, it is being fed to the filter circuit, and then this filter circuit, it is connected to load resistance RL across which output is taken. And this is the output of the rectifier which we fed to the filter circuit. This is pulsating in nature, but on the other side of the filter circuit, the output is purely DC. So this will be the output in case of when we connect filter circuit to the rectifier output. And now there are 4 types of filter circuits, and those 4 types are, we will discuss all one by one. So first type of filter circuits is series inductor filter, which is also known as series L filter. Second type is shunt capacitor filter or C filter. And the third one is choke input filter. Here both L and C, they are connected, so it is also known as LC filter. And fourth one is where one LC filter and one C filter, the 2 filters are connected, and the shape is like that of pi. That's why it is known as pi section filter. So today we will discuss first filter circuit, that is series inductor filter. What these filter circuits do? These filter circuits, after connecting in series with the rectifier output, they provide us the regulated voltage by reducing the ripple factor. So in all of these filter circuits, we will analyze the effect of these filter circuits on the ripple factor of full wave rectifier and half wave rectifier, that how this ripple factor, it varies in each of the filter circuit. So this is series inductor filter for full wave rectifier. So here you can clearly see that AC input, it is being supplied to the transformer, primary coil of the transformer, and with the phenomena of mutual induction, we will get the desired output, that is known as rectifier output. And we know that what is the shape of the rectifier output in case of full wave rectifier. And then the output of that full wave rectifier here, it is being supplied to inductor which is connected in series, and then load resistance RL across which output will be taken. And here the output, it will be approximately purely DC output. So in this filter, inductor L, it is connected in series with the load resistance RL. And this inductor L, what is the function of this inductor? So as you can clearly see, at this point, the rectifier output, it contains both the components, AC component as well as DC component. But at this point here, we have only DC component. It means this inductor, it blocks the AC component but allows the DC component to pass through it. So what is its function? Inductor L, as we all know that, as you have studied in year 10+2, that inductor, it opposes any change in the current flowing through it. How? By producing induced EMF in it. So what happens when current through the inductor, it tries to increase, then this inductor, it opposes that increase in current. How? By storing energy in it in the form of magnetic field. And in the same way, when current through this inductor, it will try to decrease, at that time, what it will do? It will oppose that decrease of the current. How? By taking that already stored energy away from the magnetic field. Means in both the cases, it is trying to maintain the constant value of current. So, in this way, we can say that inductor smoothens the output current and therefore reduces the ripple factor. And we can also view this problem in another way. And what is this another way? We know that inductor, it will offer inductive reactance to the flow of current, and inductive reactance offered by the inductor is given by XL, and it is always equal to omega times L, where L is the inductance of the inductor and omega is the frequency and angular frequency, and we know that omega is 2 pi nu or 2 pi f. And we know that for DC, the value of frequency is 0. If value of frequency f is 0 for DC, then what will be XL, that is inductive reactance offered by the inductor to DC? It will be 0. XL will be 0 for DC. And what is this XL or inductive reactance? It is the opposition offered by the inductor to the current. So opposition offered by the inductor to the DC current, it is 0 because its frequency is 0. But as we know that frequency of AC is non-zero, means it is having frequency value greater than 0. So inductor L, it will offer high resistance to the flow of AC because the value of F frequency for AC, it is high and it is directly proportional to inductive reactance. So inductive reactance for AC will be high. So it means inductor, it will block AC, whereas DC will pass easily through it and AC will be blocked. So in this way, the time period for which current flows through RL, it is lengthened by the presence of inductor, which means in simple full wave rectifier, what happens is that the period of conduction of diode D2, it starts only after the current in diode D1 stops. But in case of inductor or in case of full wave rectifier with inductor, the period of conduction of diode D2, it starts before the current in diode D1 stops. So which implies that voltage through load resistance RL, that is output voltage, it never drops to 0. As you can see, here is the output voltage, this blue one, it is the output voltage with filter, with inductor filter, and it never approaches to 0. It is always non-zero. So it is because of the presence of inductor, because the period of conduction of D2, it always starts before the current in D1 stops. So this is the output of series L filter, and this curves shown with the red pen, they are the curves, these are the curves of output curves of full wave rectifier without filter. And here this is the peak value of the output, that is plus Vm. And we know that what is the DC voltage VDC in case of full wave rectifier? It is 2 Vm by pi. So it will lie somewhere here. This is this dotted curve, it represents this VDC, which is equal to 2 Vm by pi in case of full wave rectifier. This we have already calculated in the characteristics of analysis of full wave rectifier. So the output of inductor filter, it is this, which is shown with blue pen. So here you can see that the peaks of with filter and without filter, they don't coincide with each other. It is because with the presence of inductor, the voltage in case of inductor, it lags behind the voltage without inductor filter. And it is approximately purely DC because the AC component, it is very small as compared to the AC component in case of output without filter. So now we will analyze the inductor filter and we will calculate the value of ripple factor in case of full wave rectifier with the inductor connected in series with the load resistance. So to calculate ripple factor, we know that the formula of ripple factor is gamma is equal to IRMS to ratio of IRMS and IDC. So we have to calculate IRMS and IDC. For that, what is the output voltage of full wave rectifier? It is expressed by using Fourier series, and output of the full wave rectifier with L filter, it is equal to V naught is equal to 2 Vm by pi minus 4 Vm by 3 pi into cos 2 omega t minus 4 Vm by 15 pi cos 4 omega t and so on. So as you can clearly see that in this equation number 1, which is the output of L filter, here this 2 Vm by pi, this is the value of VDC. So this first term in this equation, it represents the DC component. While the other components, all other components, they contain the frequency. It means they are the frequency components or AC components. Because for this component cos omega is 0 for DC. So cos 0 will be 1. But here omega is non-zero. It means all the other components, they are known as AC components or frequency components, and they are also known as harmonics. So if this is the DC component, that is VDC is equal to 2 Vm by pi, then what will be the DC current flowing through RL? It will be VDC by RL. So put the value of VDC here. And for XL, we know that XL is equal to omega L. So the value of XL, it will increase with omega. Means inductive reactance will increase with the increase in frequency. So here the frequency of this component is 2 omega t, this is 4 omega t and this is 6 omega t. Means frequency is increasing as we move from second harmonics to third harmonics to fourth. So as the frequency will increase, inductive reactance or the opposition offered by the inductor to these frequency components, it will also increase with the increase in frequency. It means inductor, it will offer very high opposition to this component than this. And this inductor, it will offer high opposition to this component than this. So in this way, very high opposition will be offered by the inductor to the higher harmonics. So their contribution will be negligible, or these higher harmonics components, they will not be able to pass through inductor. So that's why inductor will block all of these components, higher harmonics components. So we will retain only this, because the frequency for this lowest harmonics, it will be small, and if frequency is small, then inductive reactance offered by the inductor to this component will be small. So in this way, higher harmonics can be neglected. So how the output will be changed? So output of inductor filter, it will be given by DC component, that is 2 Vm by pi, and AC component, that is minus 4 Vm by 3 pi into cos 2 omega t. So this is the AC component of the voltage VAC. So what will be the AC current in the output? It will be VAC by, because in this AC component inductor will also play its role. So that's why resistance will not be RL, it will be Z. Z is the impedance. So it will have contribution of RL as well as omega into L. But here omega is 2 omega. So here XL will be 2 omega L. So it will be force omega square L square. So this is Z, put this Z value here and value of this VAC here. And why this phi factor is introduced here? Because we know that in case of inductor, current lags behind the voltage. So this IAC current, it will lag behind the voltage VAC by angle phi. So what will be the total current flowing through the load? It will be IL and it will be the sum of IDC plus IAC. And what is IDC? It is 2 Vm by pi RL minus what is IAC? It is 4 Vm by 3 pi cos 2 omega t minus phi divided by impedance, that is Z, is equal to root RL square plus 4 omega square L square. So what will be the ripple factor? It will be the ratio of root mean square current and DC current. And what is the relation of root mean square current? It is peak value of current divided by root 2. So what is the peak current in IAC? 4 Vm by 3 pi into this root RL square plus 4 omega L square. This is the peak value of current. And divide this peak value of current by root 2. So this peak value of current, it is divided by root 2. It is equal to root mean square current divided by what is the value of IDC? It is 2 Vm by pi RL. Now cancel the similar terms. So the similar terms will be cancelled out. So here take this RL square common. And when you will take this RL square common from the square root, then you will have this RL, and this RL, it will be cancelled out with this RL, and we have this. And now in case of inductor filter, the value of L is large because only then this inductor will play its role significantly. So if the value of L is large, then this 4 omega square L square, this quantity, it will be greater than this RL square. Then this whole quantity, it will be greater than 1. So you can ignore this 1 as compared to this and then take its square root. It will be 2 omega L by RL. So this. And this 2 and 2 will be cancelled out. So the value of ripple factor gamma is RL divided by 3 root 2 omega L. So what are the conclusions regarding the performance of inductor filter? First conclusion is that the ripple factor gamma is directly proportional to load resistance RL. It means we need the small values of gamma. And for small values of gamma, we have to use small values of RL. And small values of RL means high value of load current. So this implies series inductor filter is suitable only for heavy load. Heavy load means small value of RL but high value of load current. And the second conclusion about the performance of inductor filter is that ripple factor gamma is inversely proportional to inductance L of the inductor. And it implies large value of L means smaller values of gamma. So we always use large values of inductance L in the inductor for small values of ripple factor gamma. So this is all about series inductor filter with full wave rectifier, and this article is very important. So in the next lecture we will discuss about shunt capacitor filter.